Suppose that we were asked to show the following, that the square root of 1 plus the square root of 8 is approximately equal to 31 over 16, and it asked us to use differentials to show this. So how exactly would we do that? Well, the first thing that we are going to do is come up with a function that we can use to help show this. So the function that we're going to use is f of x is equal to the square root of 1 plus the square root of x. Okay? Because notice that if I can evaluate f of 9, because I know what the square root of 9 is, right? And then I can help use this, and because square root of 8, if I just change that by 1, I'm only changing the x by a value of 1, and that should be pretty close, right, to the function's value at x equals 8. So this would be a good approximation if we used differentials or linear approximation. So first, let's kind of show what we were talking about evaluating that function at f of 9. Okay? So at f of 9, we have the square root of 1 plus square root of 9. This is now just 1 plus 3, which is square root of 4, which is equal to 2. Okay, great. So before we get into more of the arithmetic, let's take a look into how do we show this with differentials, excuse me. And let's start by graphing just a y and x axes, and I'll draw a function that looks somewhat like this. This is f of x. Great. And I'm going to draw a tangent line in green at one point here. Let's go something like this. Okay, so this is a tangent, and it's tangent at about this point right here. I'm going to call this x naught. Okay, so if I were to move a little bit to the right or to the left, let's go to the right in this case, a little bit to the right. Let's go a distance of about this. Okay, and this, let me go up here. Now this is like some change in x, right? So I want to show you that, okay, on the tangent line, the change in x, we will call this lowercase delta x, okay? But this is the same change in x as the change in x to the function's value of the red function. So I'll call that capital delta x, okay? Okay. Now let's take a look at the y values, the change in y. Okay. Similarly, this small differential delta y, so this is the differential right here. This is delta y. See, this is the change in y of this tangent line. Okay. And then we've also got that change in y of the function, right? And we'll remember we're calling this capital delta y. So a couple things here let's point out, okay? Notice we've got that delta x, capital delta x is equal to lowercase delta x. So the differential of x is the full change in x of the function. We've also got that that lowercase delta y, so the differential of y. Well, this would be equal to, it would be that slope of the tangent line times the change in x, right? So the slope of the tangent is just the derivative at that value x naught times the change in y, right? And that would be, or the change in x, excuse me, right? Because slope is rise over run. Multiply that by the run, and we just get the rise, which is the delta y. But that change in x, this is delta x, right? Let's write it as differential of x. Okay, great. We also can say, if you look closely, notice that for very small changes in x, that capital delta y is approximately equal to the differential y, right? So we can say that the change in y is approximately equal to the differential of y, okay? So throwing this all together now, if we did have a function x and we're evaluating it at some point, x plus a little bit extra x, so x plus a small change in x, this would be equal to, well, you can think of it in a couple of ways, right? It's the function's value plus the delta y, right? That would make sense. Okay. And actually, let me just put on the graph what point that we're referring to here. This right here is f of x plus delta x. Okay. But we know that delta y is approximately equal to that differential of y, right? And that differential, we just said, would be equal to f prime of x naught times that differential of x. So here we've got a little bit of an equation that we can use to approximate a function's value at some point, some x plus change in x, and it's in terms of differential. And you'll notice that this is very, very similar to linear approximation because these concepts kind of go hand in hand with each other. Okay, so now that this makes a little bit more sense, you can see that our initial value, x naught, and actually this should be f of x naught plus delta x. We can see here that we chose our x naught to be equal to 9, and our delta x is actually 1 in the negative direction. Okay, great. So now, well, what else do we need for this? We need a f prime, right, of x naught, and f prime is in our formula. So let's find the derivative of x. Well, this is going to be equal to, all right, well, we've got a big rational function, so we'll do half times 1 plus square root of x to the negative half, and this is chain rule now. We've got to multiply this by half times x to the negative half. Okay, that seems right to me. Okay, so now we are left with 1 over 4 times the square root of 1 plus square root of x times the square root of x. Okay, this seems correct to me. Oh, and I am not even on the page. Sorry about that. So we should get this as our derivative. Okay, we can find that f prime of, well, actually, before we see what we're evaluating this at, remember, if we are looking for f of 8, because f of 8 is approximately square root of 1 plus square root of 8, right? This would be equal to f of 9 plus negative 1, right? And this would be equal to, well, I should say this should be approximately equal to f of 9 plus f prime of 9 times that delta x. In that case, that delta x is negative 1. Right? So let's find what f prime of 9 is. And f prime of 9, just plugging this in, we get 1 over 4 times square root of 1 plus square root of 9 times the square root of 9. We are left with 1 over 4 times square root of 1 plus 3. That is square root of 4. And this is 3. We are left with 1 over 4 times 2 is 8. 8 times 3 is 24. Right? Does this make sense? Let's double check that this math is okay. Okay, yeah, this is looking good. So what's left? We just need to plug this in, right? So we know f of 8 is roughly equal to, well, f of 9 we found was 2, right? Right there. Okay, this is 2, and this is minus f prime of 9 is 1 over 24, and this is going to be 48 minus 1 over 24, just rationalizing this, and we're left with 47 over 24. Great. And this is us showing the results. And I actually just realized there's an error in this question. This should not be 31 over 16. This should indeed be 47 over 24. So let's change that. Great. But process of the question, exactly the same. Just recapping. We're finding a function that we can use to approximate the differential by, or approximate this value by. We are going to use these differentials, these delta x's and these change in y's, and we know that since the change in y of the function is approximately equal to the differential in y, then we can come up with this equation for f of x plus delta x, and then we just need to choose an appropriate value for x and delta x. We evaluate the derivative, plug it into the equation, and then we can show that f of 8 is approximately equal to 47 over 24.